performance concrete, so I'm asking why. Lower water cement ratio means smaller, hopefully smaller but broken capillary pores, but smaller anyway, capillary pores. Smaller capillaries can absorb water to the height, whereas larger capillary, the atmospheric difference between the pressure means it can't really absorb it too far. So would high performance concrete perform well in chloride or carbonation environments? Carbonation, possibly. Chloride? Answer is yes, it will. Yes, it'll have a smaller capillary, so therefore the transport will be much deeper. But it might have broken capillaries, which means deep enough but not really deep. Okay. And the other aspect of it, which I forgot, high performance concrete often have higher amount of replacement materials. Therefore, these reactions, it's not just transport, I mean there's reaction as well. So there'll be reaction phases happening as well, which means it'll stop it. And yes, the other part is the capillaries are small, so the amount of water transported is very, very small. Okay. So if you design it with proper cover, you're okay. So bear that question in your mind. When you're using high performance concrete, you can expect problems due to capillary suction. Okay. Corrosion may not be a possibility because it might be broken, and if you have decent cover, it's not going to happen. But other problems can arise. First of it is if it transfers salt and if the salt evaporates, efflorescence it's called. Then the water brings the salt in, a couple of millimeters, it's broken capillary, it deposits there, but water can escape, the salt can't. So it might actually have a cracking potential. Quite often, because of the amount of cements that you're using and the binders that you're using, it will have plastic cracking, shrinkage cracking, and it might also have other form of cracking due to internal pressures. So you have to be really careful on how far you want to go in the high performance. The only way I suggest to go high performance is by testing. Make it, test it, be happy with it, and then evolve it. Okay. So coming back to it, so transport mechanism is the deciding force, which is determined by the microstructure and the way you make it. Curing has a significant role in this game. Once the transport mechanism can be controlled, which means you're controlling the alkalis coming from outside, it's not the alkalis in the concrete, controlling the water coming from outside, controlling the oxygen, the chlorides, the carbon dioxide, and all of it. There's a reason why they're repeating at times. Okay. If you can control these factors, you can control if you control the alkalis coming in, then you can control the alkali attack. You talked about caustic soda plant. There might be external alkalis coming in. Okay? So you can avoid the alkalis attacking the sulfates. If you control the water, you can control the alkali aggregate or alkali silica reaction as well as alkali attack, because alkali can't walk into a concrete. It has to come with the water. And water is an essential part for corrosion. So if you control that, you control the corrosion. Oxygen is an essential part for corrosion. You control that, you control corrosion. Chlorides, they don't move in air, they move in water. So if you control the water flow, or water-based flow, then you're controlling the chlorides. Okay? Up to anything between 25 to 50% relative humidity, the pores will have a line of water, so it can transport chlorides into it. We've seen it before, but the rate of transport will be much, much, much lower. It will still transport. Okay. Remember the cast iron that I said. It will transport in cast iron, which means it will transport anywhere. Carbonation, if you control the transport mechanism, you control the rate at which carbonation comes in, you can delay the onset of corrosion. The reason these things are highlighted under a white banner, because they have the potential to change and have a reaction with the cement. Chlorides combine to form a binding systems, and they convert the aluminate part of it to Friedel salt. carbonation forms calcite or calcium carbonate within. Sulfates form gypsum. They all have pore blocking effect to a certain level, and after that it just goes cracking, except the chloride part. So all of these mechanisms, deterioration mechanisms, results in cracking, whether that's micro cracking or macro cracking. Things that you can see is macro, the things that you can't see unless you look in an optical microscope or below is micro cracking. And the micro cracking will affect your transport mechanism, because a cracked concrete means it's a free fall, it's a highway. Okay? Ultimately, the cracking depends on your fracture strength. So if you want to make a good concrete, in my opinion, don't put a lot of cement in it. If you put it for the right reason. Find out a mixed design that gives you the lower transport mechanism. First thing. Find out a concrete that can give you a good fracture strength. Provide sufficient cover. If the cover concrete decides to remain in place and decide not to move, it's not going to corrode, because it has to yield for corrosion to progress. It'll start corroding, but it'll stop. So good cover, reasonable strength, low diffusivity. This is your best bet to making good concrete. Are we clear? Brilliant. This is an old stats, you can ignore it. Okay, do you have any questions so far? We're going to start from here. If you want to take a picture, you can. And that's what I was referring to. So the smileys means they're good practice, and the frownies mean they're not really a good practice. Okay, it's a bit unrelated, but anyway, let me put a relation to that. Provide sufficient cover. The minimum cover is specified in your standard, am I right? Okay. But the minimum cover should be designed by you as the designer. And I'm fairly certain in saying that most prestigious projects, the contractors will go for higher than what's prescribed, because it's in their interest to provide a better concrete, and they will do that. Too much high means the cover concrete has no steel in it. You have to remember that part. Too much high means you're now crossing the boundary where things can crack. If you don't have steel to contain the cracking, you can have micro to macro cracks. Okay, so you need to be very watchful of that. I would say 60 to 70 would be the maximum that you should try. If you are confident with the technology, like say fibers or anything else is used, or polymers, then you can go more if you wish. But the Norwegians would say they use 80 mil cover on their oil rigs, and they've been using that for a long enough time. I don't know how, but they probably have the technology to do it. So just be watchful of exceeding certain values. Placing and curing is extremely important, because diffusivity, when it starts, it's very similar to strength behavior. So, is that the definition for strength here? Okay. So, compressive strength, time 0, 1, 3, 7, 28, 180. Compressive strength, can you help me to draw the compressive strength graph? So I'll start with 0. Okay, let's say this is MPa. And then it will, depending on what you're applying the concrete to, some people will say they will have a lot of strength in the beginning. So you might actually get a figure like that, okay? Yeah, generally. So by 28 day you would have achieved quite a bit of strength, but even after that it will continue to cure, hopefully, and give you better strength in the long term. Okay, but it might flatten at that point. What will be the diffusivity? So if I draw diffusivity in the same line, diffusivity is a measure of the connected pores. Therefore, it's a measure of the flow through the concrete, whether that's flow of oxygen or carbon dioxide or chloride. So if you put diffusivity, would the diffusivity be high at the beginning? Yes. When you mix it, it's just water, isn't it? So it'll be the highest. Okay. It won't be infinity, but it'll be the highest. And then it will start to come down. Am I right? Okay. What we know is this coming down business can last up to 25 years. But the rate of change will be much lower after 90 days. It won't be much. So curing has a large part in deciding how fast this comes down. Okay. It's not possible to just super cure it. It probably is possible, but I don't think the technology is out there yet. But you can control the curing so that you follow the path. If you don't follow the path, it probably will flatten somewhere here, and you don't get the diffusivity that you need. Okay? So that's the role of curing. I wanted to say something, I forgot. I'm sure it'll come to me. That's true. When do you specify a property for concrete? Do you specify compressive strength for 28 day, or do you specify for 1, 2, 3, 7, 14, 28 day, or even more? What's the best age to specify? How many for 28? Be honest. So 28 day. How many for more than 28? In ACI, there is agreement that 56 day is the better measure, because the more replacement materials you use, you're going to get a bit of delayed. You're going to get a bit of delayed strength increase, and that's known because your replacement materials will have a slower reaction uptake. So 28 day is not necessarily the best to represent it. Diffusivity is exactly like that. 28 day is absolutely not the best. I would prefer to go 180 days. It's a bit unreasonable, but that gives you a very typical pattern. Okay? And I don't expect it to change more than 10% after that. Six months is a long time. If you're curing properly, in 6 months you would get almost the lowest diffusivity. It will continue to lower for certain. And we also know that this will increase with time, depending on the exposure, depending on internal reactions, cracking, everything else. But this time scale, you're talking about years and years and years. And that's why I said at the beginning, no structure is designed for eternity. Everything will have to break. Happy enough? So see if we can shift from 28 day to 56. The moment you shift that from 56 to 28 to 56, you're also sending the industry a signal saying we're in the long-term game, not in the short term. For precast and other kind of applications, they are looking at 1 day strength and they're looking at 1 day property because they're casting it, they're moving to site. Okay, but that's business, so they need to be looking at how to cure them. And they will clearly be looking at how to make the concrete better. Okay. So don't fall into the same trap of faster is better, and not necessarily. If you want to do that for any number of site reasons, you have to find a way of getting them to cure. Okay. So those are the things that we need to say on that. So throughout the presentation, I'm going to talk about test methods and sensor systems, okay? If you want to read further about the test methods, there's n number of textbooks. Some of the textbooks that I would recommend is from a guy called John Bungay. There's a lot of Johns in here. Okay. John Bungay is a very balanced person. He's a structural engineer, he's a durability person. So his books will be at the balanced level. John Broomfield is a corrosion specialist. So his books will have a corrosion flavor in it. He's an absolute authority on that. Nick Carino is from US, from NIST. And he's also broader, but he's more into structural aspects of it. So if you want somebody to have a express opinion on strength or cracking related tests, read Nick's publications. Most of them will say testing of concrete. So the best thing to do is just find their publications and they look at what you want to do. These guys have testing of concrete is a book that they release. John also have corrosion in concrete. It's quite a good book. Other than that, so this is for teaching and for undergraduate to master's level maybe. But for master's students who are looking to research on certain things, my suggestion will be to go for RILEM books. Okay, RILEM Committees produces what's called state-of-the-art report. State-of-the-art, star. They're called RILEM proceedings. There's 92 proceedings at the moment. Each proceeding is a collection of work from a lot of authors, and they're contributing to one area. So RILEM NEC refers to near surface evaluation of concrete. Basically, they're testing the cover concrete only. Okay, so if you're looking at tests for cover concrete, look at the RILEM NEC proceedings, and you will see some of the instruments that I'm mentioning in the RILEM NEC. Okay, there's a RILEM NEC on concrete compressive strength, and it's still not NEC, RILEM Technical Committee on Concrete Compressive Strength. They had a proceedings already. The committee is still ongoing because it's a very important area of work, which means they'll be producing more work later on. Okay, that's by a guy called Dennis Bryce, BRYSSE. So if you're in the strength area, look for RILEM's work on that. If you want a reference, just email me and I'll get you that. For general purpose application engineers, I suggest you download a copy of ICE, Construction Materials Manual. There's a lot of them, and you can download what's required for you. So there's an ICE construction manual for NDT, non-destructive testing. I can possibly show you how it looks a bit later. Okay. That's written at a level that the tables in it is directly comparable for site testing. So if you do the testing and you refer to the table, it'll tell you if these values are such and such, concrete is good, bad, whatever. So it's designed in that way that it's applicable. So theory aside, I'm going to go for concrete testing first, and then I'm going to explain the sensor systems. There's so many sensors available. And I think in the future you can create your own sensor system. I don't think it's really complicated business. It is concrete after all. So as long as you're monitoring diffusivity or ionic transport or pH, you're probably going to get everything that you want. So maybe I'll let you design a sensor. The only difference why the universities can afford to come up with all these things is because we have the luxury of time, whereas others don't. They're working quite hard enough to earn, whereas we get money to read and to write. Oops. So, my testing will be characterized into these areas. So all of this together conveys the transport mechanism. Absorption, capillary absorption. Permeability, where that's air or carbon dioxide or oxygen. Diffusivity, where there's a concentration difference. So this means there's a pressure difference that you're looking to assess. This means you have a drier to a wetter zone of capillary absorption, where water and salt are brought in. That means you have a concentration difference. Okay. And fracture strength. The reason I'm going to these two, as you've seen the table before, the big diagram before, those are the major aspects. Okay. Fracture strength is important, and the mechanisms are important. Okay. And within that, I'm going to explain some of the instruments that I worked in closely with. This was developed by a guy called Adrian Long years ago, 30 years now. Adrian Long was a professor in Queen's University. He still is. He's 75 at the moment. The top one, autoclam, was developed by his student, Professor Mohammed Bashir, also worked in Queen's University. And this was brought in. This was brought in 80s, and that was brought in the 1990s. And the next one, the permit, was my job. In 2000 we released it. But we were still going by this scheme. That's our scheme. We're going by that scheme. We're looking to assess everything. But one of the main differences is that we were very keen to assess it on the structure itself. Because we do know that the difference between laboratory cast and the site cast, and we know the difference between them. Therefore, we wanted to be able to assess it on the structure as much as possible non-destructively. It is a challenging thing. So I'm going to go for fundamental of the test, not that test, any test, and then I'm going to explain how the test works. It's not a sales pitch. So you always have to remember that if we can create this, you can create better with time. And that's why I keeps telling you that it's the time is what the essence is. Okay. So I'll go to the basics of where we built the idea and how we came to that idea. There are competitors for autoclam. There's a test called Torrent. Professor Roberto Torrent developed that test. It's commercially available. It's actually a very successful test. There are no competitors for permit at the moment because it's a field test, and same as that, there are hundreds of competitors for limpet. And that's exactly what my point was. With time, other people will research and come up with better and faster solutions. For those of you who are students in here, it's your responsibility to evolve it. A test will only be successful if it is affordable. And otherwise it'll remain and it'll stay in the university laboratories. I'm aware of it. Everybody's aware of it. So I'm looking towards permit to see how we can evolve it. Okay. I may not have the answers, but you may get the answers in the future. Okay? Fair enough. That's now mine. So going at, let's look at absorption first. Absorption is the property by which a dry material will absorb something into its capillary. So how can you determine a test for absorption? Can you draw a test for absorption? Draw the schematics of a test for absorption.